Okay, so we had the Stinespring dilation theorem last time, and so in that theorem, this was stated in an algebraic context, which means that you represent a general completely positive map by a representation and what is called a compression, this V star V operation. Right? And so most of the time, actually, the algebra that we're looking at is a complete matrix algebra, right? Finite dimensional, maybe even. So then, in order to use that theorem, you have to know what the representations of this algebra are, and that's basically today's topic. So number. So the setting would be that we have one Hilbert space, and well, two Hilbert spaces actually, and a representation of B of H in B of H hat. This is exactly what Stinespring dilation gives us, or that comes out. And so we'll have a closer look at how to get such representations. So basically, the story here is that we have a set of operators in this larger Hilbert space, or in this H hat Hilbert space, that algebraically behave completely like the operators on H. For example, it could be that we've identified certain operators that somehow make a qubit, right? So a two-dimensional system. So there could be a situation in which we are given some operators. For example, there would be operators A and B and B of H hat. Well, both are indifferent. And we have that A squared is equal to B squared is equal to 1. So you could think of two projection-valued, two-valued observables, and also they amplitude. So this basically that defines a representation, right? So we have two such operators with these properties and these relations, and then we would have pi of 1 would be A, pi of 2 is B. No, that's rubbish. Sorry. Okay. So basic, how did I memorize these relations? Well, I know what the relations for Pauli matrices, and then clearly these are algebraic properties of Pauli matrices. And if I have any such set, then the third one would be maybe BA. The sign is somewhat arbitrary, right? So this means that we have a representative of every Pauli matrix, and of course of the identity. We just take the identity. So that is a representation. Right? So in our large system, we've identified the operators that are the observables that belong to one qubit. Right? So claim you can split the Hilbert space. H, that would be C2. Depends on the rest, some rest. And the operators, the operators of the representation basically act here. So let me state this formula. Right? Oh yes, I should say that so this is an isomorphism, and pi of any operator under this isomorphism is just become A times. So the qubits live in this, so that these observables live in the first tensor factor, but there's also a complement, there's a rest here, there's another Hilbert space that describes the rest of the system. So let's formulate that theorem. Now there's a difficult word appearing here, normal. That is a continuity condition for the representation, which is only relevant in infinite dimensional cases. Basically, it means that this is a continuous map in a topology that is defined by the expectation values with so-called normal states, that is with density operators. But just ignore that. But if that is what you have to put in if you want to think of H especially being infinite dimensional. So when H is finite dimensional, you don't need that. So then there's a Hilbert space. Call it K, like previously. K and a unitary operator. So the shorthand notation I used with the isomorphic equality sign is now spelled out by using this unitary operator, such that pi of A equals, now let's check. So this is A times the 1, and we need the U here and the U star there. Right? Okay. So one way to think about this is in the language of representation theory would be there is only one irreducible representation of D of H. And any representation is the direct sum of those. And so there's some multiplicity, and this multiplicity is measured by the space K. It's another way to state the same thing. So K appears sort of as a multiplicity space. So for example, if we take a one-dimensional projection in H and its representative, this will not be a one-dimensional space in general, but this is precisely counting multiplicity, right? So this dimension could be larger. And so this is exactly how the proof goes. So define So this is sort of our basic model of K. So we find that as a subspace of H, and now we have to define the unitary operator. So you can think of so these things are a basis chosen for H. So we have to define the unitary from there to this tensor product, and therefore it's clear that this gives a direct sum decomposition of the space H hat. Right? So maybe call this K K1, and Kj would be I of J H hat. Right? So every vector would actually be decomposed into this direct sum, and that is already a decomposition that has something to do with just a vector in H. Right? Only the components of that vector will have values in this space. Now these are always basically the same space. Why is that? So we clearly have that pi of ij goes from kj to ki. Why? Well, this is just the thing that is projected by this jj ketbra. So then we have a representation. So we can multiply these together, and then we see that we end up in pi ij on an arbitrary vector phi, and that is a vector in ki. Right? So we really have a direct sum decomposition of our original Hilbert space H hat that is done by this representation. Okay, so but this basically tells us how to define the unitary. Right? So a general vector in H is now decomposed phi is a direct sum phi j, and this is in kj. And our unitary will just map this to the basis vector j, tensor some, well, actually this component, but interpreted via these isomorphisms as an element of K. Right? So just writing this out, so phi j, it would just be phi of j phi. That is just the j component of that vector with respect to this big direct sum. And but we can map this back to K1, which is what we call K, and that will be the corresponding component. So actually, U phi will be the sum of J. So this lies in the first Hilbert space. So we want to go to H tensor K, right? So this is the basis of H. And the corresponding vector will be this, essentially this phi j, but we want it to be in K, and therefore we use one of these maps that are the representative of the matrix units to get us into k, right? So this is in H, this is in k, which is, right? So if I operate on that with another pi of 1, 1, nothing changes, so I'm in that subspace. Okay, so there are a couple of things to check here, and according to our brief conversation just a few minutes ago, I should do these things more explicitly. Right?
Yeah.
So let's do that, okay?
Do we need a faithful representation?
Okay. One answer is every representation is faithful. If we I kind of assume that the identity goes to the identity, right? And this is something that we do need. So I have to admit I included that in my understanding of representation, but this is not general usage. So. So a unital representation would be the word for that. That would insist on that property. Right? So okay. So this cannot be 0 in particular. And then the statement is that there is only one representation, and that this is automatically faithful. Okay. So but actually, I'm proving this just now. So I'm just computing all the representations. So from that you will see that, representations of this form are clearly faithful. And so basically it's just amplifying with multiplicity. Okay, so let's do the scalar products here. So first of all, I think it is clear that this is onto, right? Because, but okay, one other. Now, this is a sum of scalar products of product vectors. So here in particular, so this begins with a k. I might as well write it out. I know it's unreadable, but think of this as 3 dots. So right. So, but there's a k here in front, right? So the whole sum collapses to j equals to k. That's what the first term just says. And then we have a sum over j, scalar product of pi of 1 j pi of 1 j sum. Okay? Now, of course, we take the adjoint here. And so this comes over as pi of the corresponding thing star, but the star, we can pull the star inside, which just changes this around. So we get pi of j 1, 1, j. Now the scalar product of 1, 1 can be kicked out. So we have JJ. So this is pi of some JJ. And that's clearly the identity, right? So, sorry, the sum is inside. So this is the identity, and pi of 1 is 1, so this is pi. And we're done. So if I had, at this point you see that we need a unital representation. And also, this is the point where normality strikes. So normality actually means that the representation is continuous for increasing families of increasing families of operators, and upper bounded. So in a Hilbert space, if I have an increasing family of operators, for example, a sum of positive terms, then this whole thing is bounded by the identity. So it's a bounded but increasing sequence. Now, if I look at the expectation values of that, this will clearly be a converging set of expectation values, and that just means that all expectation values converge. And they converge, in this case, this is exactly what is meant by convergence to the identity. So this infinite sum here, possibly infinite sum, when H is infinite dimensional, this possibly infinite sum converges in this sense, in the sense of expectation values to the identity. Now, there are representations of B of H, of an infinite dimensional one, that are not normal, and that actually have the property, so purely singular representations are defined by the property that the representative of any finite dimensional projection is 0. Compact operators get mapped to 0. So in that case, the pulling in the sum here over J would not work. Right? It would be, all these terms would be 0 actually. And so under pi, every one of these terms would be 0. And we couldn't make this conclusion, obviously. So you see how normality and the unitality is used. Yeah, so if I don't assume unital, what would the theorem be actually? So then clearly there's always one representation that respects products and adjoints, which is the 0 representation. This is not unital, of course, right? But it properly satisfies all the other requirements of a representation, of a star representation. It's also normal, actually. So it's just 0. So we have the 0 representation, and that would be allowed. Now, the only thing that could happen now in addition would actually be a direct sum with a 0 representation. So there's, how do we see that? Well, pi of the identity, by the algebraic rules, has to be a projection. It would be the 0 projection for the 0 representation, but in general it's just some projection. So this whole game would work, and the representation would actually go to operators on the subspace to which this projection projects. And then everything would go through, and on the rest, the representation is just 0. Right? So this is, that is what, if I drop this, the only thing I get in addition is a direct sum with a 0 representation. Okay. So what we've proved here is that well, we haven't proved that this is unitary so far. We have only proved that it's isometric. Right? U star U is 1. That's what we proved. So is U star also 1? Well, U star is then also a projection, and it is then also the identity exactly when this map is onto. And we only have to show for this that it has dense range. Right? Now, the range is in H tensor K. So it contains an arbitrary basis vector tensored with some element phi j. Now, which elements phi j can occur? Well, by mapping back from K, we see that anything in Kj can actually occur. So we get an arbitrary basis vector, and then the full range of K that is possible, that lies in the range of U, and that is everything. Right? So you could always expand and get a representation like that. So that is onto, or at least has dense range, which is good enough. And that together proves that this operator is unitary. Now, how about the representation? So we have to compute U star A tensor the identity U. And we still have to check that that relation for the representation. That is our main target there. So this is actually well, let me just put vectors. That's something that I frequently do, right? Identifying an operator by its matrix elements, and that is good if you have a definition of U that is defined on a vector, so then you can plug that in straight away. Right? So that's what we do now. Of course, this U goes to the other side. So we get sum over J and K. And then, as before, right, we have J, K, and pi of 1, J. No, wait a minute. Yes, pi of 1, J, A. No. Okay, I was doing too many steps at this time. So let's just write it out. So this is sum jk. And then here we have j. Tensor pi of 1j. And there's a phi at the end. Yeah. That's the scalar product of this one. Okay, so this is I've already written this as a draw. Now you have a tensor product. Kets and draws are operators. So so this just becomes the sum over jk, j a k. So a j a k. That acts on the first factor, and then on the second factor we get this scalar product that we had before, pi of j 1 1 k. Okay. So so again, this goes out, and we just have the representative of the matrix unit JK. Right? But so this goes out, and we can write this as psi pi of the sum which is just the expansion of A in matrix units. So you see the sum over ket bra jj, the identity appearing here and there, and just put in the identities there, and then you just simply get so by comparing for arbitrary psi and phi, we've proved this identity. So we actually do have just a tensor product. So that would conclude this theorem, so that we erase a few balls. Are there questions about the proof? There are more infinite sums there, right? And in the infinite dimensional case, there is some additional care that you have to take at these points. But again, this is covered by would be covered by normality. Okay, so we can plug this into our version of the Stinespring dilation. Right? So, corollary, that is theorem plus Stinespring. That's T and B H out. In. A normal, same kind of continuity, normal C blank. Then there is a Hilbert space. we are kind of expecting that, right? So this will be our dilation space, but now the new space that we get is just the space K. An operator from E well, that is all actually, right? And so the proof of that so there was an isometry in the Stinespring theorem that we call V, or well, it's an isometry if the channel is unit, right? But there was an operator V in the Stinespring dilation as shown as proved, and now we just get UV instead. Now we take this thing and call it V, and that's already the proof. Everything is just exactly. So So we have two completely positive maps, and with T and T minus T1 CP. Then there is a unique, there was this rather Nicodemus sort of derivative, call it F1. This is now an operator on K. And that lies between 0 and 1. And T of T1 of A is represented as V star of A tensor F1 V. So I just plug the F1 into the second factor here. So the reason for that is so if I take E of I look at E of H1 tensor the identity on the second Hilbert space as a subset of right. So I have a composite system. So our system Hilbert space is a tensor product, and then I look at the observables just of the first system, which I can consider as observables of the whole system by tensoring with the identity. That's a standard procedure. Right? So so this is a subset. And now and this is actually exactly the range of the representation. So now we have in this dilation space, H hat is actually such a tensor product, namely of H out tensor K. And I'm stating a general fact here, that's why I call this 1 and 2. So the range of the representation are all exactly these operators that have something in the first factor and nothing in the second. That's how this particular representation works. And now in the general comparison theorem for Stinespring, I have to compute the commutant, that is all operators that commute with all these guys. And so this is what I have to do. I have to compute the commutant. So, well, this is equal to this stuff on the other system. So actually, this kind of complement, I cited this previous theorem as identifying a complement for a subsystem. Right? So I have a subsystem whose observables behave exactly like, well, multiply and have adjoints exactly like the operators on H1, like type 1 system of the type that is described in H1. And then I can find another system that is its complement. Well, this is the way to directly find the observables. Anything that commutes with all these guys will be of that form. How can we see that? So this is a general fact, and it's an important fact. So, but once I have that, let's just check that this goes through. Right? So the comparison theorem, as stated, says there is an F1, and this F1 which is an operator on H hat on the dilation space, has to commute with the whole representation. But then this identity would tell us that this is of the form 1 tensor F1. Right? So it's actually something, the F1 of the previous theorem is actually 1 tensor F1, and I rename that and multiply these two things together that way. Right? Okay, so this is the only thing that is actually needed here to complete the proof. So I'm inclined to say this is obvious now, but let us do it. So you've seen this trick many times. So I can expand any operator on the whole system by considering it as a matrix whose indices run over the first basis labels of the first Hilbert space, and then some operators which are in H2. Right? And so let's simply do the commutator of this kind of operator with an arbitrary Kepler, an arbitrary rank 1 operator. I guess that's, maybe there's a more elegant way to state it, to do this, but this will work. So we look at the commutator, which we know is 0, of any KL, that's the identity. So this will be the sum over I and j. K and L are now free labels. So the first term gives us, well, let me just write it out. K, L, I, J. Tensor Aij, right? And yeah, let's do them separately. And the second term is
Does it make sense to take these two together?
okay. So let's just so this kills one of the sums, the I sum. Right? So that's the sum over j. J is equal to K, so that drops out. So let's follow this one. I and sorry, I have to here I have to I has to be put equal to L. So there's an L here, and here we get I L tensor. Now J has to be put equal to K. Okay. So these are this is a row of ketras where the first element is fixed and the second runs over all possible values, and this is the same for a column. Right? So the column is fixed and the row runs through. So most of these basis elements don't have an intersection, so the corresponding coefficient has to be 0. Right? So if you think of this, then this is K, and this is J, L, K, KL. Huh? So this immediately tells us that this particular ketra appears only in this sum and not in that sum. But these are a basis of the operators, so the corresponding basis element has to be 0. So we conclude that A I K is 0 unless, or let's say for I not equal to the other guy, which is L. Yes, unless and A J L no L J is 0 or J not equal to K. So we cannot make a conclusion here about the AKL matrix element. That's the only one that we cannot identify with 0. And the reason here is quite clear, because then this sum has an intersection, and for that we cannot say much. But K and L were arbitrary. Right? So one thing that I don't get somehow. So certainly this means that if we put actually k equal to L and arbitrary, then we find, and we let this run, then we find that all off-diagonal elements are 0. Right? So, so now that the thing is diagonal, and we can simplify the commutator a little bit. Right? So Aij is Ai, let's say delta Ij. Ai, and Ai is just some other operator. We still have to show that they are all equal. Yeah.
But I think what you've shown already shows that the diagonal elements are also 0. I mean, if you
But that's not true, actually. That's not true,
Okay.
because the identity is okay.
Okay, sorry.
Yeah, so we have to, how have I shown that? Let's check whether delta ik is okay. So then
If you want to show that akk is equal to 0, you can use the first conclusion on the board.
yeah, but maybe that is okay. Maybe that was a lie. So actually, what we have is there is a 0 here, right? So if L is equal to K, then at the KL place there is a 0, and we are sort of multiplying this AIK with this pattern, right? Where we have a 1 here and a -1 here, and then we sum up everything. Yeah, but I think this is correct, right? So you could choose another L, but not K in this argument. That's where the exception comes in. Right? So in this argument, as long as different. Right? Because then the corresponding coefficient in that sum will actually be 0, and therefore you don't get a conclusion for this one. So let me just simplify the commutator with that. I mean, we still have to argue that if you accept it so as far as this, then actually we could take the diagonal, we could take k equal to L and get this sort of conclusion. Right? Maybe that would be simpler. That gives you all off diagonals equal to 0. Now, we do have to take the off diagonal elements here, the k not equal to L as well, and we definitely have to use them in order to conclude that these A's are all the same. Right? So if I plug that in, that's a delta. So this sum is actually also killed, and then we have the commutator is KL this is a delta Lj, so this is KL. This is also KL. So the commutator of A with KL tensor 1 is KL. Tensor, and here we get the ALL, so a little AL, and here we get the AK. And for this to vanish always, we just conclude that the A's have to be the same. So and that is just saying that A is one tensor. Right? So then this is delta Ij, probably one tensor, and this element is always the same. So actually here you see that you couldn't, of course this is not ruled out, would be disastrous. Okay, so this proves that this computes the commutant of B of H inside another B of H. Right? So next item. So one thing that we can also do today is connecting that back to the other form of a completely positive map that we have. Right? So
Why from this fact about the commutant we actually get the corollary?
I did that mostly with handbraking, right? So they this is the corollary. Now there was I proved the comparison theorem last time, where you get an operator F1, but of that operator you only know that it commutes with a representation. But now, so this tells us it has to be of the form one tensor F1 and F1 arbitrary. So that's, yeah. Okay, so we look at the Stinespring representation. So such a T can be written as T of X is some K alpha X K alpha So we already proved this using the Choi matrix, but and the K alpha were corresponded to the rank 1 operators in the Choi isomorphism. Okay? So here's the proof. It tells us a little bit more how this works, namely, so the V, so introduce. So we just choose any basis in this space K, and then we know that V goes from H in to H out tensor K. So we can expand everything in terms of that basis. Right? How does this work? So actually we write V as v phi, let's say, is the sum over alpha now. This is the basis label here. And the expansion coefficient would be an element of H out. Right? So this is a vector in that tensor product space. So we fix the basis in the second space, and that leaves us a component in the first. Right? So there has to be some operator, some vector in H out. And this vector now depends, obviously, in a linear fashion on phi. So in other words, this vector that we have to plug in here is a linear function of phi, and that means there is an operator, k alpha phi. Right? So in this reading, the k alpha are exactly the components of V. Right? So if you have this Stinespring isometry, this has some components. These I would naturally call these V alpha. These would be like the components of V that I get by expanding this kind of object for a basis in the second factor. Now, if I plug that in, I conclude that let's just compute the T of just a V star X tensor 1 V. So this is I have the same problem with having a cat sitting in there. Yeah, I think one could write this as V is A alpha tensor alpha. But then you kind of have to know where the argument goes. It's a slightly ambiguous notation. But anyway, if I write it with a vector in, the first vector on that side, let's say phi psi, as usual. So this is a V acting there, so we get k alpha phi tensor alpha, just a basis element, x tensor 1, there's a second sum over beta, k beta psi tensor beta. So again, now everything is neatly written in terms of tensor products. The outer tensor scalar product here gives us a delta alpha beta. So we get just one sum over alpha. I can star this to the inside, so I get phi k alpha star x k alpha, and the psi is there. And this is the representation form. Right? So the Krauss form, the best way to think about the Krauss operators is components of the Stinespring isometry. And all the arbitrariness that you have there comes from choosing this basis. Right? So there are a couple of things we learn here. How many Krauss operators are there going to be? I think we had this already in the Choi version, Choi proof of that. So the Choi matrix is an operator, a density operator on H in tensor H out. Right? So think of the picture, pure state, one leg passes through the channel. So you have the one copy, the pure state is on H in tensor H in. So we have H in tensor H out. So the product of the dimensions is the upper bound on the rank that I might need. And in some examples, you do need that. Right? So the dimension of K
is less than and so you can always get by with this number of cross operators. You can write redundant sums of cross operators. That is, you find a set of, so all you need in order to get a representation is that a collection of vectors which have this property. So a basis will clearly do that. But you could also take some additional elements phi in there, make them linearly dependent phis. Right? So as many as you wish, actually. And each one of them would give an operator like that. So so that is cross decompositions. In one-to-one correspondence with such things, with collection of vectors. Phi alpha in K, with only the normalization condition some phi alpha. Phi alpha is the identity. And then this would allow you to decompose decompose your T into the sum of such positive things, but there may be way too many summoners. So the parsimonious way to do that, I mean, the most with the least cross operators would be, of course, taking the basis. And that's the usual thing. Now, if you have chosen your cross operators, if you do it like that, then actually the different cross operators, if you right, so this collection of the phi alpha goes to the k alpha, and including linear dependencies. So one way to reduce the number of cross operators is to take them linearly independent. So if you, whenever you take an overcomplete system here, right, so more vectors than a basis, then some of the vectors can be expressed as linear combinations of these basis vectors, which means that the corresponding cross operators also have this property. So the set of cross operators would not be linearly independent. So you could, if you have your collection of cross operators, your channel is maybe given in this form, then throw away everything that is, express every cross operator in terms of the other ones if you can. That's a linear combination, right? So then phi alpha would have to be a linear basis, and this condition would actually force it to be orthogonal. So all cross representations with a minimal number of cross operators, and this minimal number is just a dimension of k, are actually related by a unitary choice, because all bases are connected by a unitary choice. So if number of k alpha is minimal, which means it's equal to the dimension of k. This normalization condition actually forces to take an orthonormal basis. Right? then the phi alpha have to be orthonormal basis. And every other representation, every other cross sum as a beta prime equal to sum alpha u alpha beta, well, v beta alpha, whatever. Alpha with a unitary matrix simply because bases are related like that. Right? So, okay, so this gives us a little bit more detailed information than we had before. I guess you could also get this out of the Troy representation.
But in the last representation, you need to augment the set of cross operators with 0 operators. Is this correct?
No, the minimal number is uniquely defined. That's what I mentioned.
Ah, yeah.
And then the cross, if you have a minimal cross cross sum that is with the smallest number of terms, dimension of k,
Okay.
then your collection of vectors satisfying this has to be also normal.
I was reading every other cross sum I was reading as even of larger cardinality. Because a similar statement is true in this case as well.
I meant this.
Yeah, okay. Other minimal cross sum. Yeah.
So yes, if you have another one, then you can still do it like that. But the u then is, what is it? Isometric, right?
Yeah, or you can just augment the original set of cross operators with 0 operators in this thing. In this
Yes,
case. It's the same.
That's another way to do that. So it would be unitary, but you only need, so there's some zeros here, but you could also say there's an isometry from k into a larger space. In which you do that. And that would then be, I mean, you had the minimality conditions for all dilation theorems, right? This would be a non-minimal dilation. So it would not satisfy this condition that the vectors of which we know the scalar products span everything. So you add some zeros, and that gives another possible representation. Okay, so I guess no. Let's just do the ancillar form also. So this is another form of the Stinespring dilation. I should get by with a single bar. So any T from D of H out to H in so now I'm thinking of channels, right? So with one. okay, so this is pretty clear, right? This is just another channel. And it has, apart from the official inputs and outputs, it has additional inputs that we call the ancillas. And so this is K in, K out are the ancilla spaces. And so I prepare some additional ancillas, and this means that you just trace out the output system. Right? And of course, sorry, of course you can write anything like that, but the point here is that T twiddle is unitary. And here you put in a pure state. That's also a condition. So this is what I announced, that that you can represent the general channel in terms of a unitary building block and an operation of adding some ancillas. This is a tensor product with the input state. And then tracing out some other ancillas at the end, which is symbolized by this identity here. So these ends are sort of fixed. This is tracing out or putting the identity in the Heisenberg picture. And this is just adding a pure state. So how do we get this unitary? Well, basically, this unitary is the Stinespring isometry. So I think I'll do this by hand waving. It's not interesting enough to really do it in all detail, is it? Okay, next time. But basically, it will be the Stinespring isometry, only that if we take this representation, we only need that part of the unitary operator that acts on phi. So there's only one dimension that is needed of this whole big unitary, and we can invent the rest in an appropriate way. And that's the only thing we have to check. Actually, our space K is this guy. This is the old K. And the K in has the appropriate number of dimensions, and we'll see that this always works. Okay, so see you on next Wednesday.